All right, welcome back. Let's get straight into it, shall we? Okay, here's the result that we wrote up last time. And this is basically what we're trying to build towards in this series of videos. We're trying to show the reasoning for coming up with this idea in the first place. That was what we've just been through. And then I'll talk now about how this actually is proved mathematically. And once it's finished, I'll give a few open questions. Okay, let's get right into it. Now, I'm still working through the replacing the crashed videos, so you're going to see me do the old redo trick with the document, and I'll get back to live writing once I catch up. Okay, so here we go. So this is part 2 and a little bit of part 3, a priori estimates and global analysis. And the main thrust of this entire section is to show that the maximal time of existence is infinite. Okay. Now, we're talking about existence time, we're talking about controlling the behavior of the flow so that it doesn't become singular and stop existing. You know, that's basically what we're trying to do when we're saying we want to prove that the flow exists for all time. We want to bring to a contradiction the claim that at some finite period of time, everything has gone pear-shaped. You know, the flow has developed what we call a singularity and cannot proceed any further. Singularity would be somewhere where the curvature is infinity, or a tangent vector is not defined, that sort of thing. And normally that's coupled with a change in topology. So you can imagine these things occurring. You remember we have this loop type configuration as one of the pictures that I drew before. You know, this picture up here, there's this little loop. So if you did flow this curve, you could flow this curve, and we would expect this loop to disappear in a point. And once it disappeared, it would disappear in a point in finite time. We would expect it to happen in finite time, although there's no proof yet. And once it disappears, at the very moment it disappears, the flow will not exist smoothly anymore. And that would be called a singularity. Okay, which is one of the reasons why we had to rule those guys out, because they will wreck our result. They'll make it not true. Okay, so before we do any of that high-powered stuff, first we need to get back to basics, and we need to talk about how everything changes with time. All we know so far is the position vector. We need to know a lot more than that. Okay, so let's calculate how geometric quantities change with time. And the main geometric quantity that we're interested in is the curvature. Now, what is curvature anyway? Well, I said before that curvature is a measurement of bending at a point. It is, that's true. This is the curvature scalar. You can tell it's the curvature scalar because it's a lowercase k. It doesn't have that half arrow on top. It's not the curvature vector. I also said that the curvature scalar is the normal component of the second derivative of the curve with respect to arc length. And that's true. And I also said that the second derivative is like an acceleration to give you some kind of an intuition. But I'm going to now give you another kind of intuition. Basically, the curvature is a quantity that is invariant under rigid motion. So that's a loaded sentence. So invariant means it doesn't change, and rigid motion means a composition of rotations and translations. Basically, what you can do in the real world with your hands without, destroying something is rigid motion. So, for example, I've got handy a real. This is not a real whiteboard, but anyway, this is a real whiteboard eraser which I've got in my hand, and it is not flat. It has some curves here. There's some curves here, and right now I'm just moving it around, and you can just observe that the amount that it's bending at one point doesn't change whether this whiteboard eraser is here or here or here or here. It doesn't matter, and it doesn't matter if I turn it or rotate it. it won't change how much it's bent here. Now, if I could squeeze it, if I squeeze it or break it, then yes, it will change. But that is not a rigid motion. And that's basically due to the hypotheses of Euclidean geometry. So in other geometries, you are allowed to do different things. Sometimes you are allowed to stretch objects in a certain prescribed way. Other times you are allowed to reflect them, invert them, things like that. Okay, anyway, Euclidean geometry, we have this curvature quantity. Okay, and so these other geometries also have other invariants, which is, anyway, subject to a different story. So we need to know how the curvature changes with time. That's going to encode all the information we need about our curves. Pretty much. Almost all. Okay, this is the curvature. The other quantity, and this sounds funny, but the other quantity that we need to worry about is the position vector itself. Because the if you think about it, rigid motion, we have these fixed parallel lines. So you're not really going to be rotating. Your curve is not really going to be rotating very much, or translating anywhere except up and down. Just up and down. You can think of these as like I don't know, like sliding up and down a ladder. And if we control the curvature, then we will have controlled the curve, but only modulo or up to rigid motion. So it's not going to be enough to conclude stability of the line unless we also control this translation direction. So that's what the gamma is for. The gamma is to control this translation direction. If you have gamma and the curvature, then you're good to go. Okay. Another important quantity is ds. So ds is the arc length element, and the arc length element is used to determine the length. Now, the length itself is very well controlled on these flows, except possibly for the free elastic flow, where it can grow. Sorry about that. A little bit of family responsibility. If I need to go again, then I have to. It's just what happens. Working at home. All right. So we're talking about these a priori estimates and these geometric quantities. So this ds is the arc length element. It tells you how long the curve is, and it's also important, especially when we're trying to take advantage of facts like the reduction of length that is a characteristic of the curved diffusion flow. Okay, this is called the arc length. And other key geometric data are the Frenet-Serre frame. So this is the tau, the tangent vector, and of course the nu, the normal vector. And you can choose the normal vector to point up or down, but normally what we pick is that the curve runs from left to right. So we have a well-defined left and right from the parallel lines that we have as boundary conditions, and normally we take the tangent vector to go left to right, and then the convention would be that the normal vector would point upwards. But it doesn't have to. It's a choice. Okay. So apart from the curvature, which is obviously very important, another quantity that you've seen has been its derivatives, first derivative, second derivative, and so on. These are also going to be important. Okay. So we need to work out the time derivative of the curvature. How's that going to work? Yes, basic Euclidean invariant is the curvature, and let's see what it is for at least the curvature vector. It's two derivatives. Okay. Now, what exactly are these arc length derivatives? They have a formula, and it's like this. This is sort of a type of shorthand, really, for this derivative operator. And what is this quantity? Well, this is 1 over the length of this vector. What is this vector? This vector is the derivative with respect to u of gamma. And you might be like, whoa, where did the u come from? And the answer is, it's always been there. The u is this variable inside here, inside this minus 1, 1. This minus 1, 1 is an interval, and it's the parameter domain. So that's where gamma takes its inputs from. It doesn't actually take an input unless you reparameterize it. It doesn't take an input from 0 to its length. So the arc length parameter is not technically parameterized by that in this statement. Okay, so this is where the u comes from. Okay, let's go back. Okay, which is where you have this expression here for the arc length derivative. Okay, so if we want to take a time derivative of this curvature vector, then what exactly is our task? All right, time derivative of this curvature vector, which is time derivative of 2 derivatives of gamma. Basically, what we want to do is hop this derivative over these arc length derivatives. Hop the time derivative over the space derivatives. Now, if you've done some calculus, some multivariable calculus, then you will have seen that normally this is fine. But not in this case, because in this case we have this coefficient and we cannot simply ignore it. It's not a constant with time. So we need to deal with this coefficient. Okay, hop, hop. Now, why, I should explain why that's a good idea at all. After it's hopped over twice, we're going to see ddt of gamma. And that is something that we know. The flow has been prescribed to us. Here is one of the flows, the curved diffusion flow, and you see it's the time derivative that's been prescribed, or at least the normal component. And free elastic, similar story. Okay. So how do we swap the time and space derivatives? Basically, we need to work out their difference. You want to swap them. We want to work out this difference. It's not going to be 0. It's going to be an operator, and it's written like this with the square brackets, sometimes called a Lie bracket, or I should say often called a Lie bracket, but here we're going to call it a commutator. Okay, now this is my terrible handwriting for commutator. Okay. Okay, consider a general flow. So we're going to do this in general because why not? And now there's a little typo here. This should just be ddt of gamma. I will fix it later. And what we do is we take this is just shorthand. This is just any kind of speed. I put a minus sign here because I just prefer it that way. I like the formulas better when they have a minus sign in front. And then here, this is a tangential term. Now, you've got to be careful with this tangential term because sometimes it will be there, sometimes it won't. And it depends on your boundary conditions. Because that tangential term for us, it is going to need to be 0 on the boundary because we have parallel lines with a 90-degree angle. So if it is not 0 on the boundary, then it will violate the boundary conditions, won't have a solution. And I'm not saying that this tangential term is definitely there. My purpose with including it in these calculations is just educational. I just want to show you how you deal with the tangential term because I think it's quite cool. Some things that happen are quite nifty. Very cool. Okay. Right, so we need this tangential term to vanish on the boundary. This is the notation for it. So we use the same little partial derivative symbol here, but it means boundary. So this means t on the boundary. That's what this symbol, this notation means, 0. Okay, and I've still got that typo persisting, but it will be removed. In general, if you see typos that I have not corrected, please let me know, because I'm only human and I would like to at least fix them in the video description or the conference booklet or something, even if I don't make more videos or repair videos. Okay, so the trick is, I've already started the calculation here, so let me just go backwards a little bit. The trick is to look at this quantity by itself. Now, this is not exactly a geometric quantity, because this is just the arbitrary derivative that was given to us of the curve gamma. It's not the intrinsic arc length derivative. The arc length derivative has geometric meaning because it tells you the derivative along the curve with respect to length along the curve, which is exactly what you want. This ds is a Euclidean arc length derivative. That's what we want. Whereas this du is completely arbitrary. It might be very nice, could be the same as the arc length derivative as long as the length matches up. It could be, or it could be completely different. It can be arbitrary. It's arbitrarily bad. Anyway, but it appears as this coefficient, as like a correction factor to this original derivative, and so we want to work out its evolution first. That's the trick. Okay, now we use the square here because the length of a vector squared can be written as a dot product or a scalar product of vectors, and that will be helpful algebraically. Okay, first we're going to calculate this in two ways. First, we do the derivative with respect to it as a power, as the chain rule. So the 2 comes down the front. You're left with the quantity itself multiplied by its time derivative. That's one way. That way is finished now. Now we're going to use the second way. Second way to calculate it is to write it as the vector product, the dot product, scalar product, inner product, whatever you want to call it. This tells you the cosine of the angle between these vectors multiplied by their length. That is what this means, and that's equal to this quantity over here. Now, why is that obvious? It's not obvious if you've done, I think this would be in your high school mathematics or your first year of university mathematics, this kind of calculation. But basically, if you take the product of a curvature of a vector with itself, like this, the scalar product, the cosine of the angle, they're the same vector, so the angle is 0, so the cosine is 1. And multiplied by their lengths, well, that'll just give you the length squared. So that's why this is equal here. Now for us, it's important to know that this product is just like it's a bit like a multiplication. The time derivative will just distribute across the individual components and add together, and it's a symmetric product, so you can swap it and factorize it, which is what we're going to do. So we get this coefficient of a 2, and then you have a time derivative and the u derivative. Now, I've already swapped these guys because the time derivative and the u derivative do commute. The u derivative is a fixed thing. It's set at the start of the problem, and it does not depend on time. Okay, now we can substitute this equation up here, and I think this is where I see my error. Yep, it's gone. Oh, it was never there in the first place. Okay, now we substitute that in. Okay, so we're going to stick it in this bracket, the time derivative. Oh, it didn't get put in this bracket? Well, we'll just pretend like it's down there. So we've got minus f nu plus t tau in this bracket. And first the u is going to land on the norm. Well, it will land on the f. But if it lands on the f, right, so you get fu, then we're going to have the scalar product of the normal with gamma u. Now, gamma u is parallel to the tangent vector. So in particular, the angle that these guys make is, 90 degrees in some way. And that means that the cosine of it is 0. So the scalar product of these two will be 0. Okay, this is what I'm writing over here. If you have two vectors, like a tangent and a normal, they're orthogonal. then they have 0 inner product. Okay, so then the u will land on the normal vector here, and that will give us a tangential component, which will then give us a non-zero result when we take the scalar product with gamma. Okay, there's a formula here. And I can see I made another typo, but I think I fixed it up pretty quickly. There should be a minus here. So the u derivative of the normal, you've got to pay this weight price because you took a non-geometric derivative. It's the curvature scalar times the tangent vector. And the tangent vector and gamma u are parallel. So they're not gonna, it's not going to give you 0 as the inner product. By the way, you might say, oh, but it could be 0 because gamma u could be 0. But no, because we assumed that gamma is actually a curve, and that means that its derivative is not allowed to vanish. So u is arbitrary, but the derivative is not allowed to vanish. So that's an assumption that we have carried throughout the whole thing. Okay, and I can see I fixed up my little typo here. Okay. So the first term is, by this formula, going to be this one. And you might say, well, where's the minus sign? Well, that's because we had this minus sign up here that I just artificially put. And that's why, because I like this term to be positive. Okay, so that's all the terms there. And then the second pair of terms, when the u derivative lands on the tangent vector, we're going to get something normal, and then that'll have 0 inner product with gamma u. So the only term that contributes is the u derivative of t, which we're going to see here. Okay, so we've got tu gamma u, and that's okay, but we really don't like it because we would prefer to write in terms of the s derivative. But you can just use this formula here to convert between u derivatives and s derivatives. And you see the price you have to pay is 1 power of gamma u. And that's what we're going to do. Okay, so if we pay 1 gamma u, we can consider this to be a TS. And we have a gamma u squared. Okay, and that's the evolution of that quantity. Now, how does that help us? Well, it actually tells us the evolution of this quantity as well, because we can cancel out the 2's, and we can cancel out 1 power of the gamma, and then we will have a formula for ddt of the length of gamma u. Just like this. Right, so you've got kf plus ts. Just like that. Okay. Now, I promised that we would do the commutator. This is not the commutator. So let's get going. Why does it say ds? It says ds because we can take a little break from the commutator and already get some good information, which is what I want to show you, because this is the key information in working out the evolution of ds, or the length. And I think that is already quite interesting and worth explaining. Okay, so first up, you've got this expression for ds in terms of the original parameterization, the arbitrary one, and we can use that to define L. So here we go. So I've written it as before as integral ds, which is true, but let's write it using the u parameter so that we can pass the time derivative inside without any dramas. So you remember we had that interval -1 to 1, that's the limits on our integral. We've got gamma u and du. Now everything's written in terms of u. We can pass the time derivative inside and use this formula here, this one here, and you see we're going to get kf plus ts gamma u. Kf plus ts. Oh, there's no gamma u. The reason there's no gamma u is because we substituted this back for ds. Okay. Now, what's going to happen next? Next, we use the fundamental theorem of calculus to simplify this term. So derivatives and integrals do not cancel out. That's not true. But we know how to evaluate the integral of a derivative using the fundamental theorem of calculus. The fundamental theorem of calculus is in high school, but you probably won't see a proof until you get to university. But it's a good thing to know and to use. Basically, what we get when we integrate a derivative is the value of this function on its endpoints, usually with a minus between them. But it depends on exactly what kind of object we're integrating. But there's always some sort of fundamental theorem of calculus at work. Might be just slightly different, depends on the setting. Okay, so we've got t evaluated at its endpoints. Now for us, we're lucky because t was assumed to vanish on the boundary. So what we get in the end is just integral kf. And that's the evolution equation for an arbitrary flow of curves with certain boundary condition for length. We can substitute f. We can substitute for f the velocities inside the brackets here. You notice I already put the minus at the front, so the f is what's just inside the brackets. And if you put, for example, KSS, this one here, then you would be able to integrate by parts and use the no flux boundary condition to derive that ddt of L is minus integral Ks squared. In other words, decreasing for curved diffusion flow, which is pretty nice. That's a pretty nice result already. Almost no work. Okay, but let's keep going. Let's go back to the commutator. We want to finish this commutator. All right, so that was this Lie bracket. Now let's write out what it is. ddt dds minus dds ddt. Okay, but let's really write out what it is. Okay, so it's this expression in terms of the arbitrary derivative. And we just leave this other one alone because, spoiler alert, it's going to cancel out. Okay, now this time derivative distributes over this product first onto the reciprocal and then second onto the du. Now once it hits the du, it passes straight through and we end up with this term, but with a plus sign. Okay, so first on the reciprocal, just differentiate it like any power, and like you would any power. Okay, and you see what happened there was we paid the price of 1 power of gamma u to turn this u into an s. See, just like that. The next thing, okay, is it goes straight through the u, makes the du dt, and this first part is going to be the dds. So it's going to cancel out perfectly with this term. Okay. Right, just like that. And so they're gone. Like they were never there. Okay. So the next thing to happen is for us to use the evolution of this quantity that we've already calculated. So remember it's kf plus ts. And not just kf plus ts, but it was kf plus ts gamma u. And so the gamma u's cancelled out here. Let me just show you that. It was here. So ddt of gamma u, so you've got this gamma u factor after the brackets, and so that actually cancels out quite nicely with the denominator, and just gives you this beautiful expression. And you'll notice there's no more u's. So this is a geometric expression, invariant under reparameterization. Well, in a sense. Okay. So that's our evolution equation for the commutator, And the next thing to do is to look at the curvature. Now, I think this is long enough. I know I'm playing catch up here, but I don't want to kill you guys. So I'll say thank you very much for your attention, and I'll see you in the next one. Peace.